So last time, 8.1 was an overview of sequences and series. And so in 8.2, we're going to focus in on sequences with some more detail and some more challenging aspects. And then in 8.3, we're going to look at infinite series. And then the real fun of the chapter will honestly begin in 8.4 in terms of new work that we need to do for calculus. Okay. So let's remind ourselves briefly of the idea of the difference between a sequence and a series from 8.1. There a question there? Okay, so from 8.1, the basic idea was that a sequence is a list of numbers and that a series is just what you get when you add those numbers up. And that both sequences and series might be finite or they might be infinite. And that one of the things we're concerned with when we have a sequence is if the terms themselves limit toward a particular value so that we can have a limit of a sequence. And last time we started a little bit in 8.2 by reminding ourselves that there are limit laws which we can then apply to sequences, like the limit of a sum is the sum of the limits, etc. But the real work begins on the next page. So we're going to pick up from where we left off, which would mean we want to start on page 608, in which we have some definitions of terminology for sequences. Okay. So there's basically half a dozen words here that we can use to describe properties of a sequence. So let's remind ourselves that the notation for a sequence will be like a set bracket, and then usually an a sub n, or maybe you'll put the formula for the a sub nth term in there, but this is how we refer to a sequence. So the terminology that we're going to look at is a way to talk about whether a particular sequence that we're discussing, has certain properties or not. So the first one is to say that we can have a sequence of a sub n's and we can say that it is increasing. So what does it mean for a sequence to be increasing? Well, again, but this is a list of numbers. And the basic idea is we would say that it's increasing if each number going on along the list is getting bigger. So how do I write that? I would basically say that the n plus 1th term is bigger than the nth term for every n in the sequence. So as soon as I go to the next number in the sequence, I'm getting something larger because the sequence is increasing. How do you guys feel about that? Questions about that? Okay, so quick example. So if I had a sequence like 2, 3, 7, 11, 100, 101, 101.6, 200, and it seemed to continue. So I'm purposely writing a sequence where I don't think there's an easily or obvious pattern, easily recognizable or obvious pattern, but at least from what we can see in the sequence, it's an example of one that would be increasing. Because each time that we move to another number in the sequence, we get a larger value than we had before that. So questions about that? Okay, so let's get rid of this. All right, so it's possible that you have a sequence where the terms are getting bigger, but every once in a while they sort of stop increasing for a little bit and they kind of stay the same, but then they decide to increase some more for whatever reason. So we have a description for that. We can also say that a sequence is non-decreasing. So again, our second vocabulary word. So the only difference between increasing and non-decreasing is that it might be that sometimes you don't increase in value, but you don't go down either, and that means you stay the same. So the requirement for a sequence to be non-decreasing is that the n+1th term is greater than or possibly stays equal to the nth term. Again, so a silly little example. Let's say I have 0, 3, 3, 3, 4, 11, 11, 12, or something like that. So I can't say that this is strictly an increasing sequence because sometimes it doesn't increase, it stays the same. But what I can say is that the terms never decrease. So then we would call this a non-decreasing sequence, which means that each successive term is greater than or equal to the previous one. Questions, comments, discussion about that? Okay. So completely analogous to this, instead of not decreasing or even increasing, we could have a sequence that is going the other way. So for example, instead of increasing, we could have a decreasing sequence. And not too surprisingly, that means that the n+1th term is strictly less than the nth term, that it's going down in value. Now that may means that it's a decreasing positive number, or it might mean that it's decreasing down into negative numbers that head off toward negative infinity. The less than symbol just means that the term after the one you're looking at now will be less than the one you're looking at now. So that's vocabulary word number 3. And just like before, it might be that when it decides to change, it decreases, but sometimes it stays the same. And the only thing it doesn't do is it does not increase. Then we would refer to that as non-increasing. Again, this is just vocabulary so that we can sort of learn how to talk about sequences and have words to help us do that. And so how does non-increasing compare to just decreasing? Again, the next term might be less, but it also might be equal to the term before it. So here's a little 4-pack of words that basically just give you a way to talk about whether the values are getting larger or smaller, even if they have a tendency to pause temporarily or not. Questions, comments, discussions so far before we look at the last couple of words? Okay. Okay, the next one's easy and the last one is harder. So then we can say that a sequence, again, I'm talking about this A sub n's in all of my descriptions here. The sequence A sub n's is monotonic. Nice word. So the simple thing to say is that it's monotonic if it's either non-increasing or non-decreasing. So this literally means either non-increasing or non-decreasing. without having to specify which one of those it is. So I have a question just to try to understand this language a little bit. Does anyone believe that a sequence could be both non-increasing and non-decreasing?
So the example of a non-increasing, non-decreasing would be that cosine, or the -1 to the n, right?
So good question. And I have somebody, looks like Dima says if it's the same number over and over. So that would be an example. So let's look at both of those possibilities. So let's say it's not increasing and it's not decreasing because it's just staying the same the entire time. So let's say your sequence is just a bunch of 5s. Well, that's not increasing and that's not decreasing, so that's both. Now, if I had the alternating between 1s and -1, well, then when it changed from a -1 to a 1, that would be an increase. So I can't say that it's not increasing, that it's non-increasing, because when it goes from -1 to 1, it increased. But then when it goes from 1 back to -1, well, then it decreased. So actually the -1 to the nth power is an example of something that is neither. In fact, it would meet none of the 5 vocabulary criteria listed here. How's that sound?
Yeah, that makes sense.
Yeah. So yeah, basically the only way you could be both is if you're a constant. But usually you have things that are one or the other, but not both, because we don't really consider constant sequences very frequently because they're just not that interesting. Okay, so the only thing is that monotonic is a weaker statement than non-increasing or non-decreasing because you're not specifying which one it is. So monotonic means non-increasing or non-decreasing, even though it is possible to be both. And then non-increasing is a weaker requirement than decreasing because you're saying it could get lower, but that it also might stay the same. Whereas when you're decreasing, you have to get lower every time. So any decreasing sequence is also non-increasing. But if you specify that it's decreasing, then you don't bother to specify that it's non-increasing because that's kind of included. Is that a question there? Okay. Anyway, so we'll get more practice with these words by trying to use them on examples. But let me put on the 6th word so we can finish our little list here. So the last thing to say is that a sequence of A sub n's is bounded. And this one will be pretty important. Okay, so what does it mean to say that a sequence is bounded? So let me write the language in the statement, and then we'll see if it just makes sense for us to write that. So this bounded means, okay. So here's the language in the shortcut notation that nobody will like. Backwards E means there exists an M such that the absolute value of A sub n is less than or equal to M for all n. Again, notation, this means there exists this means for all or for any. All right, so what the heck does that mean? It means that there's some number m such that the size of the terms of the sequence in absolute value, how big the number is, whether positive or negative, we don't care, never goes beyond that number. Bounded means that there's some number big enough that the size of all the terms of the sequence never get bigger than that number. So for example, if my sequence were values plucked off of a sine function along the way, then we know that the sine function always goes back and forth between -1 and 1. So I could say that that sequence was bound by 1, because the size of the numbers that you would get if you take the sine of something are never bigger than 1. So that's the idea of a bound sequence. So questions, comments, discussions about any of these 6 words before we try to use them to describe sequences? All right, so let's look at perhaps one of their examples. This is a non-enumerated example, but it's on page 609. Okay, so let's say you have a sequence of a sub n's, and it's equal to the following numbers described by a formula of 1 minus 1 over n. So there's the formulaic way to get the nth term. And we are considering values of n starting with a 1 for the first term and heading off toward infinity. And if we try to envision this a little bit, we could write out maybe some of the first terms. So for example, if n is a 1, I get 1 minus 1, which is 0. If n is a 2, I get 1 minus 1/2, which is 1/2. If n is a 3, I get 1 minus 1/3, which would be 2/3. If n is a 4, I get 3/4. If n is a 5th, I get 4/5. Yeah. Etc. Okay, so take a look at that and let's have you think for a second, which of those 6 vocabulary words apply to describe this given sequence?
Increasing.
So do the values seem to be increasing? What do you guys think?
Yes.
Okay. And if it's increasing, then we could also use the weaker description of non-decreasing. But usually, if you do that, if you know that it's increasing, why would you give the weaker statement? And I see from the chat that there's a suggestion that it's bounded. So if you think it's bounded, can you offer a number that bounds it? And I see it there. They are always less than 1. And Wenzel's saying that as well. Great. Yeah, so you can sort of look from the statement itself, just analytically, of the formula, that you're subtracting something from 1, but the thing that you're subtracting from 1 is heading off towards 0. It's becoming smaller and smaller and smaller. So as you subtract less and less and less, it ends up increasing in value, but never exceeding a 1. Bounded, and there were good, correct suggestions that it's bounded by the number 1. So the book does a much better job than I'm doing here, or will be able to do, to also investigate this graphically. But let's say I just tried to show it a little bit. So if this up here is like a 1, actually, so then we have our values along here for n. So you could think of this as a function of x, just so that you could type it on your graphing calculator and see where the values are headed. But we do need to keep in mind that this is a sequence. We don't have all the values in between. We only have the numbers listed here. So if I graph those, I'd be starting with a 0, and then I'd be going up to like a 1/2, and then I'd be going to 2/3, then 3/4, then 4/5, which is like 80%. And so you might, and then if you had graphed the function 1 minus 1 over x, you would, see this curve here, and that you would know that your values lie on that curve, and that what we're looking at is that we have what we would have referred to back in pre-calculus as a horizontal asymptote. And so that these little yellow points that I've graphed for my values of the sequence are increasing in value. So this is an increasing sequence. It's monotonically increasing, so it never decreases at all. It always goes in one direction, but that it is bound, and you might even say it's bound above by the value 1, just to sort of give descriptive specifics. But so this is a good example to sort of think about how these terms are used. Questions, comments, discussions about this and the use of any of the vocabulary? Okay, so what I'd like to do now is actually skip a couple of pages ahead, because right when we've discussed this vocabulary is a good idea of a time to introduce theorem 8.5, because it uses this vocabulary to draw a conclusion. And then I'll go back to the previous couple of pages, but just letting you know I'm skipping a couple of pages. So on page 612 is theorem 8.5. So it states that a bounded monotonic sequence converges. That's it. Nice, simple little short sentence theorem. So what the heck does that mean? So again, what does converges mean? When you're talking about a sequence, we say a sequence converges if the limit as n goes to infinity of the sequence exists and is some number L. So again, just sort of details here. This part means the limit as n tends to infinity of a sub n, is L. That's what converges mean. And this is our sequence as a sub n's. And then we have our new words, monotonic and bounded. Okay, so just to try to wrap our minds around what this says, is our previous example something that illustrates this theorem in action? So when we were describing the example right above here, did we say that this could be described as monotonic? So there's a question, aren't all monotonic sequences bounded? So monotonic means non-decreasing or non-increasing. So let's say I have a non-decreasing sequence like the number n. So what is the sequence where it's just the number n? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. So that is monotonic because it's non-decreasing. It just keeps getting bigger. And is that bound? No, because it goes to infinity. So think of it this way. Bound means that it doesn't go to either positive nor negative infinity. Bound means that there's some limit. There's a limit above and there's a limit below. And of course, you can just choose as m the bigger of the two, to say that the whole sequence is bound by some number. So bounded basically just is a way of saying that it does not go to an infinity. And so it can be, monotonic sequences often are not bounded because lots of them go to infinity. They're not decreasing because they keep running away and getting bigger and bigger and bigger. 2, 4, 6, 8, 10, 12, 14, 16, 18. Like just, or any exponential growth, for example. Does that make sense? Yeah. Okay, so in the example we're looking at above, where we have my little ugly graph and the sequence is 1 minus 1 over n, was that a monotonic sequence? So we concluded before that that was monotonically increasing. And then is that bound? We also observed and were given that it was bound by the number 1. So according to theorem 8.5, it must have a limiting value. And in this case, we could take the limit to see if we believe that's true. Of course, it's very clear from the picture, but we could take the limit as n tends to infinity of 1 minus 1 over n. And then because as n goes to infinity, this thing shrinks away to 0, we would conclude that the limit was 1. So that does converge. It converges to the value 1. Now, I would point out by this theorem that the theorem doesn't actually tell us what it converges to or how to find where it converges or anything like that. Instead, it just says that it does converge to some number. So the question is, does it always go to the binding value, meaning the sort of the bounding m that's being used? And the answer is no, because the fact that a number of a sequence is bound by a number doesn't necessarily mean it goes to that, because if it's bound by any number, it's also bound by any larger number. So for example, if I say a sequence is bounded by the number 1, well, then it's also bound by the number 2. Because a bound just says that none of the members of the sequence get bigger than that. It doesn't say if it actually approaches or gets close to that. And let me give you an example where you would need to make use of that fact. Consider a following example to help illustrate this and also to help answer the question more clearly. So consider the sequence. Let's just do 1 over n, nice and simple. So what does this look like? 1, 1/2, 1/3, 1/4, 1/5. For those who care, this is a very, very important sequence. It's called the harmonic sequence. But in any event, we will learn more about that later. So you can look at this graphically. So it starts up here to 1, then it goes to 1/2, 1/3, 1/4, 1/5, 1/6, etc. Okay, so here's a sequence. I've given you a new example, and let's ask ourselves, how can I describe this? Let's look at the first 4 possible words that we can use. Well, that's actually, we always start with this. Is it monotonic? So I see a yes and a no perfectly. So is it non-decreasing? So we'll just focus on that one. Yes or no? Is it non-decreasing? So non-decreasing means that as you're moving to the right, it never goes down. Whereas this seems to go down pretty much all the time. So the answer would be no, this is not non-decreasing. So let's try the other one. Is it non-increasing? So non-increasing means as you go to the right, is it never going up? And since in this case we see it going down every time, then the answer would be yes. So it is non-increasing. And the definition of monotonic is that it's one or the other. So because it's non-increasing, we can say it's monotonic. And then more specifically, instead of saying non-increasing, we can actually say that it's decreasing, which is a stronger claim, because non-increasing would allow it to maintain the same value sometimes. That's not a requirement, but it allows for that to happen. Whereas decreasing says, no, you can't stay the same value. You always have to have a lower value than you had before. So most people, when they put these together, they would put these and might say something like it's monotonically decreasing. So the reason those can sometimes go together is that imagine I have something where I'm going to add just some other spots here. But I had a value here, then 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 I had a value here. So if you look at these little blue dots I've put on here, if those are legible on your screen, it could be that in the long term, you might want to somehow claim that the sequence was decreasing in overall, but it's not strictly decreasing because sometimes it goes back up a little bit or something like that. So we put monotonic and decreasing together to say that it's decreasing every time, not over the long run, that every time you get a lower value than you had before. Let's see if I can erase those. Nice. Okay, so we have, according to theorem 8.5, we do have something that is monotonic. And so then the second question, is this function bound? So Nassim is asking, isn't it also bounded? So where would you think you could bind it, Nassim? Do you think you could provide a value? By 0. Okay, so is 0 a number m such that that number is greater than or equal to the absolute value of any member of the sequence? So right, it's always larger than 0. So you could describe this and it would be okay if you said it was bound below by 0, but that's not the use of the word that we had in our definition. In our use of the definition, we need to come up with an m that is greater than or equal to the absolute value of any term in the sequence. And so as Jake points out, we could say that it's bound by 1. So I would say that this is a monotonically decreasing sequence that is bound by 1. Because note, when we say it's bound by 1, that traps it below as well, because down here might be the line that y equals -1. And by saying that the absolute value is always going to be less than or equal to 1, it forces the entire sequence to never go above a +1, but to also never go below a -1. So it can't head down to -infinity by my saying it's less than 1. By my saying the absolute value is less than 1, it traps it on both sides. So this is bound. It's bound by the number 1. It cannot be bound by anything smaller than that because the first number is a 1. And it turns out that's the littlest number we can use to bind it. We could say it's bound by a bigger number. It's bound by 10. It's bound by 1,000,000. You don't need to have the smallest possible bounding number that the sequence will allow. As long as it's bound and as long as it's monotonic, then theorem 8.5 will guarantee that it must converge to some number. So originally the question, I think, from Wenzel was about, does the binding value also, does that have to be the number it converges to? So this is an example where it's not. So this would be a sequence where it's bounded by 1 and it's monotonic, but it converges to 0. Questions, comments, discussion? Okay, so yeah, so the way you get used to using these words in a very accurate way with the way the meaning is defined is to look at examples and to try to imagine using the words correctly. And so they'll give you problems like that. And then in general, we will just use this language to sort of help us think about and do problems. Is that a question? Okay, so I'm going to erase this stuff. And try to go back to the top. I was doing the wrong order. All right, so as I mentioned, I skipped a couple of pages in order to get to theorem 8.5. So let's going to go back now. And at the very bottom of page 609, we're going to have a new definition. Let's switch to black. Okay, so what we're going to now look at is a specific kind of a sequence called a geometric sequence. We're just going to try to get this idea of understanding a geometric sequence. So we have a sequence of a sub n's. And we talked in 8.1 about a couple of different ways to define a sequence. You could either give an explicit formula for the sequence, or you could use a recursive definition in which you say how to get to the next term in the sequence. And so a geometric sequence, if I think about it recursively, is going to be a sequence in which the next term in the sequence, the n+1th term, is arrived at by taking the previous term and multiplying it by the same constant every time, which we're going to use an R for that constant. So somebody, can you please mute your mic? Somebody's sharing some sounds. It just says iPhone. So thank you. Great. Okay, so what does this mean? This means that as I go to the next term in the sequence, I just keep multiplying by the same number over and over again. So let's just look at a quick example so we can think about what's going on here without using all the letters. So an example would be, let's say I have a sequence that starts with a, I don't know, 5, and that each time I multiply by something. So we'll keep it simple and say I multiply by 2. So if each time I go to the next term I multiply by 2, then the next one would be a 10, then I'd have 20, 40, 80, and I would just keep doing this. And if it was a finite sequence, I would stop. And if it was infinite sequence, then it would just keep going like this, and I'd put my little dot, 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 and off it goes to the races. So there's a couple of things we should note about this. First of all, why is the number R used? Because the word, the letter is short for ratio, because when you're multiplying by the same number every time, that means you can see what that number it is by dividing the next term by the previous one. For example, I multiplied by 2 every time in this sequence. So then you can note that 10 divided by 5 is 2, 20 divided by 10 is 2, 40 divided by 20 is 2, and that generally the R value that you're multiplying each time will always be the ratio of the term that was forthcoming divided by its predecessor. So it's a ratio, that the ratio of successive terms is constant. So that's why it's called an R, but usually we see the formula this way. And the other thing is that we can give a specific formula for this. Namely, you can say that A sub n is arrived at by taking A sub 1 and multiplying it by R n minus 1 times. So again, just to have that formula make sense, this is the first term, this is the second term, this is the third term, etc. And that the way we got at those terms was that we took the first term, we started with a 5, and each time we multiplied it by 2. And then what you can see is, for example, to arrive at the 5th term, 80, I took a 5 and I multiplied by a 2 4 times. So the number of 2's that you multiply by to arrive at the nth position is 1 less than n. And we do that by taking the multiple r and raising it to the n minus 1th power. So we can see that 160 was arrived at by starting with the 5 and then multiplying by 2 5 times. 1, 2, 3, 4, 5 2's. And this is the 6th term, and there were 5 2's multiplied to get to that. So that's why this ends up being the formula. So this is a geometric sequence. Now, if you note, what kind of a function is this that determines the nth term? This is an exponential function. Now, if you have, when you have exponential functions, this is the base, that's the multiplier. So if R is bigger than 1 in absolute value, then if you keep multiplying by that over and over and over again, and you take the limit as n goes to infinity, then this is going to diverge. Because if I keep doubling the number, it's getting bigger and bigger and bigger, well, then it's going to head off to positive infinity or negative infinity or something like that. If I multiply by more than 1, then the value I started with will grow every time I do that. And if that keeps happening, then it just keeps getting bigger and bigger and bigger. However, so that would be an example of exponential growth. So I'm going to say it diverges due to exponential growth. And along those same lines, if the absolute value of R, and let me, and that if the absolute value of R is less than or equal to 1, actually, hang on one sec. I'm gonna have to break this into 2 cases. Let's say that it's strictly less than 1. If the absolute value of R is less than 1, then the limit as n tends to infinity of A sub n is equal to 0. And again, this is due to exponential decay. So basically, if you have a number that's less than 1, think of it as a decimal that's less than 1, like a percentage, 80%, 90%, 70%. Every time I multiply by a decimal less than 1, I'm taking a percentage of that that's less than the whole. So if I take 80% and then I take 80% of what's left and then I take 80% of that and I keep taking less and less and less and less, then that's going to shrink away to 0. That's an example of exponential decay. You can look at this graphically, numerically, any way you want to think about it. Now, I left out the idea of r being equal to 1 as an absolute value because it could be a 1 or a negative 1, so we can think about those cases separately. If r is equal to 1, then whatever number you start with, when you multiply by 1, you just keep getting the same number, so then your sequence would be constant. Let's go ahead and write this down. So then note, if r equals 1, sequence is constant, which means it converges to whatever the first term is. And if r is equal to negative 1, then the sequence alternates between a sub 1 and the opposite of a sub 1, and therefore diverges. So let's pause there and see if I've lost people along the way and anybody wants to ask a question for clarity. So these results are summarized in theorem 8.3. On page 611. All right, so let's maybe let's just consider looking at an example to try to get a feeling for what's going on. So let's say we look at example 3. We'll just look at A. And we're going to consider the sequence that's 0.75 to the n. So we can imagine what we're talking about by thinking about the first couple of terms here. So that starts with 0.5. And then for the next term, we'd have 0.5 squared, but I'm just going to leave it as that. We'd have 0.75 cubed, etc. So this is an example of a geometric sequence because each term is 0.75 times the previous term. And so the number we're multiplying by each time now is 0.75 is r is less than 1 in absolute value. So then I could conclude from our discussion that the limit as n tends to infinity of the sequence is 0. Questions, comments, discussion? Okay. So we've introduced some terminology about sequences, increasing, decreasing, monotonic, bounded, things like that. We looked at a theorem that said that any monotonic bounded function sequence must converge to a number. Then we looked at a specific kind of a sequence called a geometric sequence, in which each term in the sequence leads to the next one by multiplying by the same constant number, which we're calling r. And we've pointed out that if you're multiplying by numbers with an absolute value less than 1, then the limit of that sequence is 0. And if you're multiplying by absolute value bigger than 1, then it diverges and heads off to some sort of an infinity or bounces around. So this gets us to down to basically the last 2.5 pages of the section, and puts us in a dilemma as a class. Okay, so let's draw a line here. Okay, next. Trouble. So next step is trouble. So I'm just seeing a scroll up a bit request that might be old. So Jake, did you still want me to scroll up some to look at something? Okay. Yeah, so actually I was about to erase all this. So if you did want to see something again, now would be a good time because I'm about to erase all this as things are about to get worse.
Could I actually ask a clarifying question just real quick? Or
Yeah, that's great, please. Yeah, let's definitely do that before we get to trouble.
General statement, right?
Yes,
So
sir.
then this last example 3A that we looked at, we can say that sequence is, what was it, monotonic decreasing, and it's bound by 0.75.
Oh, that's true. Yep.
Okay, cool. Cool. I just wanted to make sure.
Because it's monotonic and it's bound, we know that it converges.
Right.
And in this case, we were even able to draw the conclusion that it converges to 0.
Right. Cool.
And let me add one detail to that. So that theorem 8.5 that says that a certain kind of sequence converges is one of those existence theorems, kind of like, you know, the extreme value theorem or something like that, where it claims that something exists, namely that the limit as n goes to infinity is some number L, but doesn't give you any help in how to find it. Doesn't give you a way to calculate it. It just claims that it exists. And so we are going to be looking at, I'm going to say series with sequences of partial sums. We're going to be looking at limits and trying to sort of say, do they converge or do they diverge? As I've mentioned before, it's going to be like C or D, almost like true or false, but instead of true or false, it'll be converge or diverge. So this theorem 8.5 would be a way that we could conclude that something converged. And we could choose, yeah, this converges, without even ever knowing what it converged to. Or I guess the English way is say, without even knowing to what it converged. This will not be uncommon in our future work in the chapter, in chapters 8 and in chapter 9. It will not be uncommon for us to know that something converges, but not to know what it converges. So it'll converge to something, but to what, we don't know. And so the theorem is helpful. And the idea is if it's too hard to figure out analytically what value it converges to, it probably means that that would be something that would be done numerically or on a calculator or something like that. So it's just kind of like sometimes we can have a definite integral of a function and we don't know how to come up with an antiderivative, but we could type it on our calculator and get a decimal as accurate as we wanted. There will be sometimes we know that something converges to a value and we don't analytically know how to get it, but we could always type it on a calculator and get it as accurately as we need because we do know that it converges. So any questions about any of this discussion so far up to this point before we get into trouble? Okay. All right, so let me do this. Let me give us a fresh page for trouble. Excuse me. Okay, so here's what we're looking at for this section. There was a little half of a page right before theorem 8.5, maybe even half a page, which was, so we have three problems that we want to deal with. The first is theorem 8.4. The next, which is the squeeze theorem. The next is growth rates. And the next, believe it or not, is the epsilon definition of a sequence limit. So for those who had some wonderful exposure to the epsilon delta definition of a limit, this is basically the same thing. So theorem 8.4, which is the squeeze theorem. Let's do this. So the squeeze theorem is an extension of the squeeze theorem that we had for limits of functions, like way back in chapter 2, that we now apply to sequences. And my usual experience is that most people may remember the name, but don't even really remember what it says, and that as you found at this point, that when we're doing limits, we don't really use the squeeze theorem that much. Even though I do remember near the beginning of the semester when we talked about limits somewhat, some people did mention the squeeze theorem. So I know you guys, some of you may have a, that's supposed to say rates. Some of you may have some working memories of that, which is great. But at this point, we're going to apply this to sequences, and this gets a total treatment of 1/2 of a page. And when I say a page, I mean not both sides, but just one surface. 1/2 of a page to remind us of this. And then it may come up occasionally and that we might use it to justify something, but not that frequently. And so for those who don't remember at all, it's a lot of work for a little bit of gain. Then the second is that growth rates was also an issue that was discussed before, not in chapter 2. I believe that was like in 4.7. I'm just going to put from 4.7 originally. So when in chapter 4 they discussed the idea of functions going off toward infinity, then growth rates talked about how quickly they went off to infinity, and then you compared functions. So they regurgitate that here, and that has exactly one page, not both sides of a page, but just one page surface. With one example. And then the epsilon definition sequence for a limit. So epsilon delta definitions and proofs and things was an entire section in 2.9, skipped by many teachers because students just can't handle it for good reason. It's just very challenging logically and notationally. And it's usually the hardest section in the book for many students for all of first semester calculus. So they reapply those concepts to extend the definition of a limit of a sequence to an epsilon definition. And again, they give this an entirety of one page. So they basically go from talking about sequences and giving definitions and giving examples to help us think about them. And then in the last, or sort of the last couple pages of the section, they quickly go off of the deep end for most students in terms of difficulty. So I'm figuring let's talk about these topics because they're in here and you might have some problems from homework for 8.2 on these. But you know, we could probably talk about this for a week or two if we wanted to go into depth, which we just can't afford to do. And we want to talk about 8.3 today, which is even a little bit more important, probably for at least 45 minutes if we can, something like that. So yeah, is there a question coming in there somewhere? The curve will protect me. Now you're starting to understand why I use a curve. Exactly. Okay, so yeah, so let's take a little peek at each of these if we can, so that at least, hopefully, if you then turn to those pages in the book and try to have a sense of what's going on, we've had enough of a discussion so that you can try to wrap your mind around it, or you can decide early on to just cut that part loose and take your loss there for however much that's in here, because it is literally only like 2 pages of the book, or 2 pages even of this section. Like, it's not even half of this section to talk about this stuff. So let's give that a shot. Any questions before we begin? Okay, so trouble number 1, squeeze theorem. So the basic idea before with a squeeze theorem said that if you had 3 functions, let's say f, g, and h, and the g function was trapped in between the f and the h function, and the f and the h function both had some limit, then the g function was forced to go to that limit as well. So what does that look like if I apply it to sequences? Well, it looks like theorem 8.4, which is on page 611. I think I wrote that up there, yeah. So let's say we have A sub n, B sub n, and C sub n. So these are 3 sequences. But for every single term of these 3 sequences, the A sub n term value is less than or equal to the B sub n term value, which is also less than or equal to the C sub n term value. And let's also say that we know that the limit of the A sequence is the same as the limit of the C sequence. They both exist and that they're the same number. We'll call it L. So basically what's going on is this thing, the A sequence is converging and the C sequence is converging to L. Well, since B is trapped between them, it's forced to converge to L as well. If these things are getting infinitely close to L and B is trapped between them, it has to go there too. So the way this is written in the theorem, so that we have this relationship and we have these limits exist, then the theorem concludes that the limit as n tends to infinity of B sub n must as well be L. So we can take a quick look at how this might make sense by looking at example 4. On the same page, because this is only half a page of material, and this is the only example they give, but let's take a look. So it says, consider B sub n is equal to cosine of n divided by n squared plus 1. And it says, find the limit of this sequence. So the idea that we would say when looking at this and trying to think about it is that having an n squared plus 1 in the bottom as n goes to infinity means that I can just sort of analytically tell myself that the bottom is heading off toward infinity, while as the top is cosine of a whole number n. So that's not a nice value. Because normally we get nice values from cosine if we put in some multiple of pi or something like that. But what we know about the numerator is that it stays between 1 and -1. So you have a number on the top that's just sort of going up and down somewhere between a 1 and a -1 as cosine goes through its bumpity ride as n goes off to infinity, while the bottom is becoming huge. So it ends up being that this, hopefully you could imagine then, because the bottom's becoming huge and the top is not, that this thing would go to 0. But how would we support that? How would we justify that other than just say, I think that's what's going on? Well, that's where the squeeze theorem could help us. Because what you could do is you could say, let a sub n be equal to a lower bound of this, which is when you have the -1. So let's say I had -1 over n squared plus 1. And c sub n be as high as this ever gets, which is a +1 over n squared plus 1. Then using these values, we can see in these cases that for every, or for all n, a sub n is less than or equal to b sub n is less than or equal to c sub n. And we can note that the limit as n tends to infinity of a sub n and of c sub n is equal to 0. Because you just have a 1 in the top or a -1 on the top and a denominator that's going to infinity. So those both go to 0. Therefore, by theorem 8.4, b gets squeezed between these, so the limit as n goes to infinity of b sub n is also 0. And they sort of make a nice graphical color-coded picture of this, better than I could scribble on my tablet here to illustrate this on page 611. So this works just like the squeeze theorem did back in, I think, chapter 2. And I think they used a similar kind of function at that time to do it. But now we're also applying this to sequences, where term by term we're trying to figure out what's going on. So questions, comments, or discussions about 8.4? Okay, let's try 8.2 in here. So number 2 trouble is growth rates. So growth rates is also something that was discussed back, I think it said in 4.7. And this, again, was about functions, and you could talk about like how quickly functions were going to infinity. And this was helpful for certain kind of limits and L'Hopital's rule and stuff like that. So what we want to do in this case is consider sequences, and they may be sequences going to infinity, and then we want to talk about basically which ones go to infinity faster or at a higher rate, or however you want to describe it. So the idea is whether one sequence grows faster than another sequence. And so they have a little discussion about this, but the theorem they have is theorem 8.6. And this is on page 614, and all of it is on page 614, including the example, the only one that they do. And so the idea was that if we want to say that we're comparing two sequences, so let's say you have the A sub n's and you have the sequence of B sub n's. And we want to, and we know that, say you have these with their limits going to infinity. Maybe positive, maybe negative, but just something where they're sort of becoming infinite. So then we can discuss the idea of whether one of them grows faster than the other. And this was defined back with functions and now will be with sequences. that we say that the B sub n sequence grows faster than the A sub n sequence if the limit as n tends to infinity of A sub n over B sub n is 0. Or the limit as n goes to infinity, that's an n, of B sub n over A sub n is infinite. So what does this mean? That basically when we start trying to classify and talk about how quickly something goes to infinity or what its growth rate is, rate of growth, think of exponential growth, linear growth, power growth, different types of growth. But that as things are growing and growing without bound, some grow much faster than others. You always hear exponential growth is runaway growth. It's so fast compared to linear growth or something else. Logarithmic growth is very slow. So this ends up being a way of describing the rate of growth, okay? So the way you compare two things to see which one is growing faster or has a higher growth rate, or however you want to describe the terms, is by considering the limit of the ratio of their terms and seeing if one basically dominates over the other. So let's look at like a simple example to try to make sense of this. So say, consider n versus n squared. So both of these go to infinity as n goes to infinity. And we can imagine to ourselves that the n numbers are 1, 2, 3, 4, 5, 6, 7, getting bigger and bigger and bigger. But the n squared numbers are 1, 4, 9, 16, 25, 36. They seem to be growing faster. They seem to have a faster rate of growth. So the idea of how we really would compare these is if I want to say that the n squared sequence has a higher growth rate than the n sequence, then I take the limit as n tends to infinity of the ratio, which in this case would be n squared divided by n. Now this is a nice simple one, so we can evaluate this with a little algebraic simplification. N squared divided by n is just n, and clearly the limit as n goes to infinity of n would be infinity. So what does that tell me, since I put the second one in the top and it went to infinity, that this one has a faster growth rate? So this is kind of like a definition of an idea from before, but it's a theorem, because in the theorem, instead of just giving you this definition, they do point this out in here, they give you a ranking or an ordering of a bunch of our primary types of expressions that we would have. And so I'm not going to try to copy the whole thing down, but let's put a few of them down here. So in the theorem, it has, let's say, for example, this is in the theorem, not all of the theorem. We have the sequence of n raised to a power, and they use these double inequality signs to compare which one is slower versus a higher growth rate. And then I'm going to put another one that looks similar to this one, but there's several things in here. They have n of p plus s. And that can be compared also to a sequence of the form b to the n. And there's some other stuff beside these and in between, but here's just a couple of things that are in the theorem. And let me point out, this theorem is exactly like the one they gave in 4.7 that everybody's already forgotten. So that's why they're just kind of dumping it on you on one page and saying, yeah, we're just taking that old theorem and now we're extending that to sequences as well. So they said we did the squeeze theorem before, now we extend that to sequences. We did growth rates of functions before, now we extend that to sequences. And then we did epsilon limits definitions before, and we'll extend that to sequences. That's why they're shoving this all in so quickly. But the practicality is that students don't really remember these things and didn't use them very much even at the time. So now it's becomes quickly overwhelming considering the small amount of page space that they devote to it. So what does this mean? So for example, the way I could have used this theorem is in this considering that I was doing here, I was trying to find which one had faster growth. And we ended up concluding that n squared had faster growth. But in the theorem, if I was able to recognize that n is an example of one of these, where the p-value is a 1, and that n squared is an example of one of these, where the p-value being 1, I have then added to that another number s, in this case a 1, then basically the theorem would tell me the conclusion that I drew up here, that this one has faster growth rate because it's to the right of this one. And if I'm comparing two of them, I look on this little list in the theorem, and the ones on the right have a higher growth rate compared to the ones on the left with lower comparative growth rates. And so looking at these two, if I have n raised to a power, and I'm comparing that to n raised to a bigger power, p plus s, then n raised to a bigger power will always have a higher growth rate than n raised to a smaller power. And that bigger than any of those would be if I chose to consider comparing those to, for example, any exponential growth function where the n is the variable of the exponent instead of the base. So n to the p plus s, those are power functions where p plus s has a bigger power, but b raised to the power of n is an exponential function in n because the n is the variable is in the exponent. And those will always have a higher growth rate. Any exponential function has a higher growth rate than any power function, as an example. Anyway, so this is what they're getting at in this theorem. Here's a little example of how you could compare things in the theorem by looking at them up on the list. Then they do an example for you where they do that for a couple of these things. And that's trouble spot number 2. Questions about that? So the big thing to take away from this is if they give you any problem where they're asking you to compare growth rates, look to theorem 8.6, and it literally lists the various functions out for you in order from smaller to bigger growth rates, and you just find where they are on the list in order to make the comparison. Okay? All right, so let's kill this off and let's look at problem number 3. I always do this the wrong way. Okay. So I would like to try to finish this in about 12 minutes, take a 10-minute break, then we would still have time. Yeah, something like that. Doable, but not comfortable. So then on page 615 is the epsilon definition of a sequence limit. So what are we talking about? If I have a limit as n tends to infinity of some sequence, a sub n, and we claim that it equals or converges to some number L. So what does that mean? So hopefully we have an idea of what this means at this point, meaning that we feel comfortable enough with the concept of a limit that we could say something like, as I go further and further down the sequence, letting n become larger and larger, and I look at the 100th term, the millionth term, the billionth term, that the values of the terms are getting infinitely close to L, arbitrarily close to L. They're approaching L. Yeah, we'll take a break in 10 minutes after I try to murder you with this for 10 minutes. Okay, so how do we describe that mathematically? That's what, basically in chapter 2, they spent 8 sections talking about limits, working with limits, evaluating limits, and then they defined them rigorously in 2.9 at the end because they knew that'd be very hard to do until we get to the end. So here's basically what the definition says with some of our little shorthand language, and then we'll try to think about it. So we say the limit as n tends to infinity of a sub n equals L if the following is true. If, and here's that upside down A again, that means for any, if for any epsilon greater than 0, then I'm going to write a backwards E. That means there exists, and I'll add that in a second, there exists some number n, which we're thinking of like, you know, 1 million, 1 billion, some big number like that. Such that, what happens? Well, basically, epsilon is a little number that's describing how close you're going to make the sequence terms get to L. And n is a big number saying how far down the sequence you have to go to make that happen. And so what has to happen? So for any epsilon greater than 0, there's some number I can find n such that when little n is bigger than the big N that I found, when that happens, then a sub n is very close to L, which we write as saying that the absolute value of their difference is less than that teeny little number epsilon that we looked at. So there's the symbolic definition. Again, this means for all or for any, and this means there exists So what kind of problems arise by having a definition as challenging as this to understand and to work with? Basically, you are given a specific limiting value of a sequence, and you want to confirm that that it meets the definition, that is the value of the limit. So we can look at their example. They give us 1. It's example 7. And if you have no comfort with these epsilon things, just come back at 240. But if you have an ability to sit through this or ask questions, then here we go. So let's say we wanted to show that the limit as n tends to infinity of the sequence, what's the sequence they use? N over n minus 1. Is equal to 1. So we could evaluate this limit. We could see that that's the case. We have a rational expression where the numerator and the denominator have the exact same powers of n. So as n goes to infinity, those are going to dominate and you're just going to get a 1. And we've looked at examples of this before. So the hard part is not actually determining the value of this limit. It's verifying that this value satisfies the definition of a limit in a rigorous way. And so the way we would do that is we would basically rewrite this using the specifics of our example before we begin the problem. So in order to so we're supposed to show by the definition. So what do we need to show? We need to show that for every epsilon greater than 0, there exists a delta greater than 0, such that when little n, oh, I said delta, sorry, I'm thinking of our other one. There exists, oh, I highlighted. Okay, here we go. For every epsilon greater than 0, there exists a capital N such that when little n is bigger than capital N, then the absolute value of my sequence, which is n over n minus 1, minus the L value, which is 1, is less than epsilon. So what you do when you apply this is you plug in the specific sequence that you're given and the limiting value that you're given. You plug those in to the stated definition to set up how you would do the problem. So the idea is that somebody gives you an epsilon value that's very teeny, and that you say, I can make the difference between the sequence and 1 be less than that teeny value, but just by going far enough down the sequence, by making little n big enough so that it gets very, very close to 1. So that's what you need to show. So how do we show that? Again, we go for what we want. So we, given any epsilon, we want this to be true. N over n minus 1 to be less than the epsilon. We want to make that happen. So we start with the goal. We want to show that this is going to happen, and we need to find an n value big enough to make this happen. And basically the way you do this is you solve for n. So first of all, we're going to be able to make little n as big as we want. We're going to be able to set some big number of n value, and then we say this only needs to be true when n is bigger than 1,000,000, or when n is bigger than 1,000,000,000, or something like that. So I notice here that if n is a 1, my little expression is undefined. And so I'm going to start out by just assuming that we know that n is going to be greater than or equal to 2, because this isn't even defined unless that's the case. So then if that's the case, then I have n over n minus 1 will be something like 3 over 2 or 5 over 4 or something like that. So I'm going to drop the absolute values, because this is always a positive number, so I don't need them. So if this is the case, I want to solve this for n. I would add in 1 to both sides and have n minus, well, actually not yet. Let's probably combine these first, I think is a little better. So first, if I get a common denominator here, I have n over n minus 1 minus n minus 1 over n minus 1, less than epsilon. So then if I subtract, I have to distribute the minus sign. N minus n is 0, and minus minus 1 is 1. So that becomes that 1 over n minus 1 is less than epsilon. And again, n minus 1 is positive, epsilon is positive. So I can multiply both sides by their reciprocal without flipping the inequality, because you only have to flip the inequality if you multiply by a negative. That would give me that 1 over epsilon would be less than n minus 1. And if I switch the order of these and add 1 to both sides, I get that n is bigger than 1 plus 1 over epsilon. So what that means is if you give me an epsilon like 1/10, then 1 over 1/10 is 10, plus 1 is 11, that I would choose an n value being bigger than 11, and then this would be true. So this tells me that I let capital N be some number greater than or equal to 1 plus 1 over epsilon. So then after that, you would write the proof. This tells me what I need to make it work, and then I would use this to make it work. And then I would write the proof